All right, good morning, ladies and gentlemen. This is the final part, the final lesson within this gas laws unit, and it's pretty short. What today is going to be all about is bringing together basically this current unit and the last one. It is bringing gas laws and chemical reactions and the math associated with that, which was stoichiometry. That's what we did in Unit 8, bringing those two concepts together. So here's the thing, okay? Reactions occur in moles. So if you come across a problem that has a chemical reaction and you're being asked to calculate something, that is a stoichiometry problem. If that stoichiometry problem involves gases, you have to ask yourself one critical question. Are the conditions at STP? Let's just review. Okay, STP means the temperature is 0 degrees Celsius and the pressure is 1 atm. If your answer to that question, am I at STP, if the answer is yes, then you are permitted to use that number. 22.4 liters is equal to 1 mole of a gas. And we did problems like that back in Unit 8, and I'm going to do another one with you in just a moment here, just to refresh your memory. So if it's at STP, it's really just a problem back from Unit 8. However, what if it's not? If the conditions of the problem are not at STP, then you're going to have to use the ideal gas law at some point. Remember, the ideal gas law is PV equals nRT. And again, I'm going to do an example problem with you. Okay, so let me change color here. Okay, so we've got an example problem in front of us here. It says, using the following reaction, and let's make sure, is this reaction balanced? Take a second. Okay, spoiler alert, yes it is. It is already balanced. And here's what the question says. It says, calculate the mass of sodium bicarbonate. Okay, stop there. Here's sodium bicarbonate. So above that, I'm going to put question mark grams, because that's what I'm supposed to solve for. Calculate the mass of sodium bicarbonate necessary to produce 2.87 liters of carbon dioxide. So I'm going to write that in here. And it says we are at STP. Well, that means this is a problem just like back in Unit 8. This is nothing new. So this is review. So let's review. So we've got 2.87 liters CO2. And I'm going to convert that into grams of sodium bicarbonate. So remember, follow the units. I want liters of CO2 to cancel out, so I'm going to put it down here. The only thing I can convert to is moles. Okay, 1 goes on the top, 22.4 liters on the bottom. Okay, then moles of CO2 to moles of sodium bicarbonate. Okay, and this was that silly little expression that I told you when you're going, from moles to moles, where do the numbers come from? They come from the coefficients, and I said how one of my students remembered that by saying moo moo cow, mole coefficient. I don't know, it's silly. Anyway, the coefficients are 1 and 1, and I'm supposed to go into grams And let me just tally that up really quickly. I need the molar mass of sodium bicarbonate. And you guys double check my math here. I think that's correct. That should be the molar mass off the periodic table. Let me just double check. Plus 12, plus 1. Yeah, okay, I think that's right. All right, then I'm going to do my dividing all the numbers on the top, divide by the numbers on the bottom. And I'm going to round for significant figures. Look at the printed problem. I want to round my answer, to 3 significant figures, so that gives me 10 point, let's make that 10.8 grams of sodium bicarbonate. Final answer. Okay, so this problem is not any different from things we did back in Unit 8. It's not any different because it's at STP, so it's just a straightforward stoichiometry problem. I can use this conversion factor right there because I'm at STP. But what if you're not? So this is the same reaction, but it's a different question. Okay, so this one says, if 56 grams of sodium bicarbonate are reacted. So before we do anything, I'm going to write that above it. 56 grams. Okay. At 26 degrees and 745 torr, how much carbon dioxide gas will be produced? And really, I should have said how many liters. I should have been more specific. Shame on me. Okay, so here's the thought process, guys. You are given one piece of the reaction, and you're supposed to solve for another. That is, by definition, stoichiometry. Now, the next question is, am I at STP? Well, look at our conditions here. All right, remember, STP standard temperature is 0 degrees. So we're not at 0. Do you all remember what the standard pressure is in units of torr? It's 760. So I can clearly see I am not at STP. All right, and if you look back at the 2 slides back, it says you will have to use the ideal gas law at some point, okay? So here is what I do, guys. Here's kind of my thought process. What I do is I say, okay, I know I'm going to be using this equation at some point. The question is, can I use it right away, or will I use it as like a second step? So I write it out and I put check marks above each variable. Are we given a pressure in this problem? Yes, we are. Check. Do we have a volume of the gas? No, we don't. I'm going to circle it because that's something I don't know at the moment. Were we given moles of the gas, CO2? No, we were not. That's another unknown. Remember what R is? It's that ideal gas constant. We always have a number to plug in for that. Was I given a temperature? Yes. So the point is, I can't use PV equals nRT right now because I have 2 unknowns. So what I'm going to have to do first is a little stoichiometry to get me from here, not into liters, but I should have drawn the arrow like this. I just want to get to moles. So watch, just watch. Grams of sodium bicarbonate. Okay, that was, I believe, 84.1. 1 mole. and they're in a 1-to-1 ratio. Okay, so I'm going to plug that into my calculator. 56 divided by 84.1. Okay, so I'm going to run out of room here. The number of moles of carbon dioxide, and I'm not going to round my answer too much because this is not my final answer. And I swear I did not do this on purpose. 666 moles. Okay, so now I'm going to put a check mark over that little n. Now I have moles. Now if you're wondering, well, why didn't you just keep going with your stoichiometry here and just use 22.4? I can't because I'm not at STP. You can only use that conversion factor if you're at STP. So now I am ready to use the ideal gas law. So I have a pressure. V is my unknown. I have a number of moles. Okay. Use your notes if you need to. The ideal gas constant for torr is 62.36. And 26 degrees, let's put that into Kelvin. That's 299. Okay, we're going to plug all of that in, and let's see what we get. Okay. And I'm going to round to 2 significant figures because the temperature only had 2, so that's going to round to 17 liters of CO2. Final answer. Okay. So just to summarize, sorry, let me put that back. When you are not at STP, you know you're going to have to use the ideal gas law. So I always write it out. Even as a professional, I write PV equals nRT at the top of my page, and I put check marks over what do I have and what am I still missing. If you have 2 unknowns missing, 2 things that you don't know, you can't use that equation right away. I had to do some stoichiometry first to get moles of the gas, and then I could use the ideal gas law. I'm going to do one more problem with you, okay, just to make sure that you've got this. If you have the note packet out in front of you, it's actually really not note packet, it's actually just a set of problems. But I want to do number 4 with you. Okay, so this is number 4 on those notes. Okay, and they've given us a balanced equation already. I'm just going to copy it over. Simple reaction. Okay, so here's what the problem says. Solid sodium reacts with chlorine gas to produce solid sodium chloride. Cool. Okay, what mass of sodium chloride, so question mark grams, will be produced if 25 liters of chlorine gas, okay, so let me write that down, at a pressure of 2.55 atm and a temperature of 300 Kelvin react with excess sodium. Don't be freaked out by that word excess. It just means don't worry about the sodium. Okay, so again, here's the thought process, guys. I've got a balanced equation. I've been given one piece of information. I have to solve for another part of the reaction. This is stoichiometry. The second question you want to ask yourself, are we at STP? The question says the pressure is 2.55 atm, the temperature is 300 Kelvin. We are definitely not at STP, so I say to myself, okay, I'm going to be using this equation at some point. It might be right away, but it might not be. That problem we just finished, we used it as the second step. But let's just see. Okay, do we have a pressure given? Yes. Are we given a volume of the gas? Yes, we are. Okay. Do I have a number of moles of the gas? First of all, what gas are we even talking about? We're talking about chlorine. Was I given moles of Cl2? No, I was not. So that's an unknown. We always have a value for R. Were we given a temperature? Yes. So can I use the ideal gas law right away? Yes, I can. In this particular problem, yes, I can. So let's do that. So we've got 2.55 atmospheres, and the volume of the gas was 25 liters. I don't know the moles. Okay. The ideal gas constant for atmospheres, 0.08206. And the temperature, how nice, they already put it in Kelvin for us. So let's solve for N. 2.55 times 25 divided by that. Okay, and I'm not going to round too much because, again, this is not my final answer. I'm going to go 5896. Okay, now, what is that? That's moles of Cl2. Okay, now come back to the original problem. I'm not trying to find chlorine. I am trying to find grams of sodium chloride. Can I use regular stoichiometry at this point? Yes, I can. Because I have the moles of one of my reactants, Cl2. Okay. Moles of Cl2 to moles of NaCl. That's in a 1:2 ratio. 1 mole NaCl. And if my memory serves, that is the molar mass of sodium chloride. And this will give me my final answer. 2.5896 times 2 times 58.5. And I'm going to round for significant figures. I want to go with 3. And that is my final answer. Okay, so what I want you guys to notice between this problem and the last one, the setup was just a little bit different. Okay, in the first example problem that I showed you, or I should say the one just before this one in front of you, we wrote out PV equals nRT, but we had 2 unknowns, so we couldn't use the ideal gas law right away. We had to do stoichiometry first to get into moles of the gas, and then we could use PivNert. In this problem in front of you, we had enough information about the gas that we only had 1 unknown, so I used the ideal gas law right away, and then I did stoichiometry to get to my unknown. Remember, guys, the biggest mistake that people do is they try to plug in values into the ideal gas law that shouldn't be there. Remember, it's the ideal gas law. Okay? You'll notice in number 4, this problem in front of you, sodium chloride is a solid. Okay? You can't plug in information for a solid into an ideal gas law. Okay, so just keep that in mind. All right, so at this point, what I would say is complete the problems in this on this piece of this note sheet. Check your answers, see how you're doing. I don't at this point know what, now that we're at the end of this gas laws unit, what I'm going to post so that you can kind of see, do you understand this material? But I will communicate with you guys via Google Classroom and or Blackboard and let you know. Okay? So I hope you guys are staying safe, and I look forward to our next lesson. Take care, y'all.